Physics has mastered the art of prediction. Given the initial state of a system and the rules that govern it, we can calculate what happens next with remarkable accuracy. We can track the motion of planets centuries into the future, predict the decay of radioactive atoms with statistical precision, and describe the behavior of electromagnetic fields in exquisite mathematical detail. This predictive power rests on a foundation of structure and dynamics, patterns that persist across time, relationships between measurable quantities, information encoded in physical states. Yet there exists a category of phenomena where this explanatory machinery encounters something strange. Not a failure of measurement or computational power, but a conceptual gap that refuses to close. The problem surfaces when we try to account for what it's like to experience something from the inside. The redness you see when you look at a stop sign, the sharp sensation of pain when you touch a hot surface, the feeling of being someone right now reading these words. This is the territory of consciousness, and it presents physics with an unusual challenge. The challenge isn't about complexity. The human brain contains roughly 86 billion neurons, each forming thousands of connections with others, creating a network of staggering intricacy. But complexity alone doesn't explain why this should be mysterious. We've built detailed models of complex systems before: weather patterns, protein folding, quantum field interactions. What makes consciousness different is that it involves something that seems to exist only from a particular point of view. There's something it feels like to be you, but nothing it feels like to be a hurricane, or a protein, or a quantum field. This distinction matters because physics traditionally deals with third-person descriptions. It tells us how systems behave when observed from the outside. Mass, charge, momentum, energy. These are all properties we can measure without reference to any subjective perspective. A particle's spin is what it is, regardless of whether anyone experiences anything about it. But conscious experience appears to be irreducibly first person. It exists only as it's felt by someone. The attempt to bridge this gap has led to several frameworks that try to ground consciousness in information and physical structure. These approaches represent some of the most sophisticated thinking in contemporary neuroscience and theoretical physics. They deserve careful examination, not because they've solved the problem, but because they reveal where the explanatory limits might lie. Integrated information theory, developed by Giulio Tononi beginning in the early 2000s, offers one such framework. IIT starts with phenomenological observations about consciousness itself. Conscious experiences are differentiated. You can distinguish countless different states of awareness from each other. They're also integrated. Each experience feels unified, not fragmented into separate pieces. A visual scene contains color, shape, motion, and depth. But you don't experience these as independent streams. They cohere into a single perceptual whole. From these observations, IIT derives a mathematical measure called phi. Phi quantifies how much information a system generates as a whole beyond what its individual parts generate independently. The theory proposes that consciousness corresponds to this integrated information. Systems with high phi are conscious, those with low phi are not. The quantity of consciousness scales with the phi value. The quality of consciousness, the specific character of an experience, corresponds to the particular structure of informational relationships within the system. IIT makes specific architectural claims. It explains why the cerebral cortex supports consciousness, while the cerebellum doesn't, despite the cerebellum containing more neurons. The difference lies in connectivity. Cortical neurons form dense reciprocal connections that allow different regions to influence each other in complex ways. Cerebellar neurons, by contrast, are organized into relatively independent modules that process information in parallel without much crosstalk. More neurons but less integration yields less consciousness, according to IIT. This explanatory success is real but limited. IIT describes structural relationships and information dynamics. It tells us which physical architectures should be associated with consciousness and provides a mathematical framework for quantifying that association. What it doesn't explain is why these particular structures and dynamics should be accompanied by subjective experience at all. Why should hi-fi feel like anything? Why shouldn't a system with maximal integrated information process and respond to inputs without any inner experiential dimension? This is where the explanatory gap opens. We can specify the physical structure in complete detail. Every neuron, every synapse, every pattern of electrical activity. We can calculate phi values with arbitrary precision. Yet the question remains, why is there something it's like to be this structure? The mathematical formalism describes correlation and organization, but doesn't seem to contain anything that would necessitate or generate first-person experience. Global neuronal workspace theory takes a different approach, focusing on functional architecture rather than information integration per se. GNWT proposes that information becomes conscious when it's globally broadcast across the brain's various processing systems. The brain contains many specialized modules handling different tasks: visual processing, language, memory, motor control. Most of this processing happens unconsciously, but certain information gets selected for widespread sharing, becoming available to multiple systems simultaneously. This global broadcasting is what GNWT identifies with consciousness. The theory has empirical support. Brain imaging studies show that conscious perception correlates with widespread activation patterns, while unconscious processing remains localized. When a stimulus enters consciousness, activity spreads from sensory areas to frontal and parietal regions involved in attention and working memory. The timing and extent of this spread predict whether someone reports conscious awareness of the stimulus. Again, the explanatory success is genuine but incomplete. GNWT describes information flow patterns and functional relationships. It tells us which computational architectures and dynamics are associated with consciousness. But it faces the same fundamental question: why should global broadcasting feel like anything? We could imagine a system that implements the entire functional architecture of GNWT. Information gets selected, broadcast widely, and made available for multiple processes without any accompanying experience. The functional description seems to leave out the experiential dimension entirely. This is the crux of what philosopher David Chalmers called the hard problem of consciousness. The easy problems, and Chalmers meant easy only in a relative sense, involve explaining cognitive functions. How does the brain discriminate stimuli, control behavior, access, and report mental states? These are extraordinarily complex questions, but they're tractable in principle. We can imagine explaining them through standard neuroscience and computational theory. The hard problem asks why these functions are accompanied by experience at all. The distinction matters because it reveals a potential limit in what physics-based explanations can achieve. Physics excels at describing structure, dynamics, and information flow. It tells us how systems evolve over time, how parts interact to produce wholes, how information is encoded and transformed. These are third-person descriptions, specifications that any observer could verify through measurement and calculation. But conscious experience seems to involve something beyond structure and dynamics. It's not just that certain information patterns exist, it's that these patterns are felt, lived through, experienced from within. This experiential dimension doesn't obviously follow from any amount of structural or dynamical description, no matter how detailed. Some philosophers and neuroscientists respond by denying the distinction. Daniel Dennett argues that once we fully explain the cognitive functions, the discrimination, integration, and reporting, there's nothing left to explain. What we call subjective experience is just the brain's model of its own information processing, nothing more. Consciousness seems mysterious only because we haven't completed the functional analysis yet. Others maintain that the explanatory gap is real and points to something genuinely missing from physical accounts. Thomas Nagel argued in 1974 that no amount of objective, third-person information about bat echolocation could tell us what it's like to be a bat. The experiential quality, the what it's likeness, remains inaccessible to objective description. Frank Jackson's knowledge argument makes a similar point through the case of Mary, a neuroscientist who knows every physical fact about colour vision, but has never seen colours because she's lived her entire life in a black and white room. When Mary finally sees red for the first time, does she learn something new? If so, what she learns can't be a physical fact. She already knew all of those. The phenomenal concept strategy attempts to diffuse these arguments while preserving physicalism. The idea is that Mary doesn't learn a new fact but acquires a new way of thinking about facts she already knew. Phenomenal concepts like what red looks like, have a special quotational structure where the experience itself is embedded in the concept. This creates an epistemic gap between physical and phenomenal knowledge, even if both refer to the same underlying reality. You can know all the physics of colour vision without having the phenomenal concept of redness, just as you can know all the syntax of a language without understanding what its sentences mean. Whether this strategy succeeds remains controversial. Critics argue that it merely relocates the problem rather than solving it. If phenomenal concepts are genuinely distinct from physical concepts, we still need to explain how physical processes give rise to these special concepts. And if the concepts are ultimately reducible to physical processes, then the explanatory gap reopens. Why do certain neural states constitute phenomenal concepts while others don't? The debate continues because we lack a decisive test. We can't directly measure whether a system is conscious. We can only measure correlates, neural activity patterns, behavioral responses, information processing dynamics. These correlates might be reliable indicators of consciousness, but correlation isn't explanation. The sunrise correlates perfectly with the rooster's crow, but the rooster doesn't cause the sun to rise. This is where some researchers turn to more radical proposals. If conventional physics can't bridge the explanatory gap, perhaps we need unconventional physics. Quantum mechanics, with its observer-dependent measurements and apparent indeterminacy, has attracted particular attention. Maybe consciousness involves quantum processes that can't be reduced to classical computation. The orchestrated objective reduction theory, proposed by Roger Penrose and Stuart Hameroff, represents the most developed version of this approach. Penrose argued that consciousness must involve non-computable processes because we can grasp mathematical truths that no algorithm could prove. This requires physics beyond the standard computational model. He suggested that quantum gravity effects might cause spontaneous collapse of quantum superpositions in brain structures called microtubules. Hameroff added a biological detail, proposing that microtubules could maintain quantum coherence long enough for these collapses to affect neural processing. The theory faces severe challenges. The brain operates at body temperature in a wet, noisy environment, conditions that should destroy quantum coherence almost instantly. Quantum effects typically require extreme isolation and cold temperatures to persist. Critics argued that microtubules couldn't possibly support the long-lived quantum states required by the theory. Recent experimental work has complicated this picture without resolving it. Studies have found evidence of quantum effects in biological systems under physiological conditions, quantum coherence in photosynthesis, quantum tunneling in enzyme catalysis, and possibly in olfaction. A 2024 study detected superradiance in networks of tryptophan molecules at room temperature, a quantum phenomenon previously thought impossible in warm, noisy environments. These findings don't vindicate orchestrated objective reduction, but they challenge the assumption that quantum effects are automatically ruled out in biological contexts. Even if quantum processes do occur in the brain, the explanatory gap remains. Why should quantum superposition or collapse be accompanied by experience any more than classical neural processes? Quantum mechanics still describes physical states and their evolution according to mathematical rules. It's still a third-person framework. The hard problem arises at the level of why any physical process, quantum or classical, should have an experiential character. Some recent proposals suggest a different role for quantum physics in consciousness, not as a computational substrate, but as a coupling to something more fundamental. One framework proposes that cortical microcolumns resonate with quantum vacuum fluctuations. The quantum vacuum is an empty space, but a field of zero-point energy with measurable physical effects. If brain structures could coherently interact with these vacuum fluctuations, consciousness might emerge from this coupling rather than from computation alone. This approach shifts the question rather than answering it. Instead of asking how neural computation generates experience, it asks how brain dynamics couple to a more fundamental physical substrate. But we still face the core issue. Why should any physical coupling or dynamics be accompanied by subjective experience? The recurring pattern across these theories is instructive. Each proposes a physical or informational mechanism: integration, broadcasting, quantum processes, vacuum coupling. Each can explain certain correlations and predict which systems should be conscious, but none explains why these mechanisms should generate experience rather than simply processing information in the dark. This might indicate that we're asking the wrong question. Perhaps consciousness isn't something that physical theories should explain, not because physics is incomplete, but because the question itself involves a category mistake. We're trying to derive a first-person phenomenon from a third-person description, which might be fundamentally impossible regardless of how sophisticated our physics becomes. Physics describes how systems behave from the outside. It tells us what happens, not what it's like for anything to happen. This isn't a limitation we can overcome through better theories or more advanced mathematics. It might be built into the structure of physical explanation itself. A complete physical description specifies all objective properties and relationships. If consciousness involves something beyond objective properties, something essentially subjective, then no physical description could capture it. Not because the description is incomplete, but because completeness is measured in the wrong terms. Alternatively, the problem might force us toward more radical metaphysical positions. If consciousness can't be explained by physical structure and dynamics, perhaps it's fundamental rather than derivative. This is the core claim of panpsychism. Consciousness isn't produced by certain physical arrangements, but is a basic feature of reality itself, present to some degree in all physical systems. Recent theoretical work has explored consciousness-first frameworks, where subjective experience is the fundamental substrate from which physical reality emerges. Maria Strum's model treats universal consciousness as a fundamental field, with space, time, and matter arising through symmetry, breaking, and differentiation. Individual conscious experiences are localized excitations in this field. The physical world becomes a structure within consciousness, rather than consciousness being a product of physical processes. These approaches face their own challenges. If consciousness is fundamental, how does it relate to the physical properties we can measure? Why do brain states correlate so precisely with conscious states if consciousness isn't produced by brains? And how do we test theories that place consciousness at the foundation of reality rather than as an emergent phenomenon? We're left with a situation where multiple frameworks make sense internally but can't be conclusively adjudicated. Physics-based approaches can describe correlates and mechanisms but seem to leave out the experiential dimension. Consciousness-first approaches can preserve the reality of experience but struggle to connect it back to measurable physics. The explanatory gap persists regardless of which direction we approach from. This might be telling us something important about the limits of explanation itself. Not every question has an answer within a given framework. Mathematics can't prove all truths. Language can't express all meanings. Perhaps physics, despite its extraordinary success in describing objective reality, encounters a principled limit when confronted with subjective experience. The question becomes whether this limit is temporary or fundamental. Will future physics develop new concepts that bridge the gap? Or does the gap reflect something essential about the relationship between objective description and subjective experience? A relationship that might not be amenable to the kind of explanation physics provides. Right now, we don't know, and recognizing that we don't know, that our most powerful explanatory frameworks might have reached their boundary, is where honest inquiry must begin. Let's try this differently. Some theories survive because they work, others survive because they're beautiful, and some survive by being neither, but being the only theories we have left that acknowledge something real. Integrated information. Theory doesn't start with neurons or computation. It starts with 5 statements about consciousness that are supposedly undeniable. Consciousness exists. It has structure. It's specific. It's unified. It's definite. From these phenomenological axioms, the theory derives mathematical requirements. If something is conscious, it must integrate information in a particular way. Not just process it, integrate it. The difference matters. Integration means the system generates more information as a whole than the sum of its parts. A collection of independent processes might contain vast amounts of information, but if they don't influence each other, there's no integration. The theory quantifies this with phi, a measure of how much causal power a system has over itself. High phi means high consciousness. 0 phi means no experience at all. The cerebellum makes this concrete. Your brain contains roughly 86 billion neurons. 69 billion are in the cerebellum. Yet consciousness doesn't seem to depend on the cerebellum at all. Damage to it affects motor control and balance, not awareness. Integrated information theory explains why. The cerebellum's architecture is modular, parallel processing streams that barely talk to each other. Lots of neurons, minimal integration. The cerebral cortex has fewer neurons, but vastly more interconnection. Same quantity of information, different architecture, different phi. This matters because it suggests consciousness isn't about complexity per se. It's about a specific kind of organization. You could have a system more computationally powerful than a human brain that experiences nothing because its parts don't integrate. You could have a much simpler system that experiences something because its architecture creates the right causal structure. But here's where the theory hits its limit. Psi measures integration. It doesn't explain why integration feels like anything. The theory identifies a physical structure, integrated information, and declares it identical to consciousness. Not correlated with consciousness, not producing consciousness, identical to it. The math describes how information relates to other information. It doesn't describe why that structure has an inside. This isn't just missing details, it's a category gap. The theory maps phenomenology to physics, but the mapping itself is stipulated, not derived. You start by accepting that consciousness has these properties. You end by finding physical systems with analogous mathematical structure. The bridge between them is an axiom, not an explanation. Global neuronal workspace theory takes a completely different approach. Consciousness isn't about integration for its own sake, it's about access. Information becomes conscious when it's broadcast globally across the brain's processing systems, making it available for attention, working memory, verbal report, and deliberate action. Unconscious processing is local and encapsulated. Conscious processing is widespread and accessible. The theory makes different predictions. If consciousness is about global broadcast, then specific brain regions should show increased activity when information becomes conscious. Regions involved in attention and working memory, particularly in the prefrontal cortex. If consciousness is about integration, then connectivity between regions matters more than activity in any particular area. These theories can be tested against each other. In 2023, they were. An unprecedented collaboration brought proponents of both theories together to design an experiment neither side could later disavow. Participants viewed visual stimuli while their brain activity was measured using functional magnetic resonance imaging, magnetoencephalography, and intracranial electrodes. The experimental protocol was pre-registered. The predictions were explicit. The interpretation was agreed upon in advance. Neither theory won decisively. Both made some correct predictions. Both failed in specific ways. The results suggested that consciousness involves both integration and broadcast, but neither framework fully captured what was happening. More importantly, the study revealed something about the limits of these approaches. They describe mechanisms that correlate with consciousness. They don't explain why those mechanisms produce experience. This is where quantum approaches enter, though not as solutions. They're attempts to locate consciousness at a different physical level. Orchestrated objective reduction proposes that consciousness arises from quantum processes in cellular structures called microtubules. The theory links consciousness to quantum state collapse, suggesting that awareness involves non-computable physics at the Planck scale. The standard objection is environmental decoherence. Quantum superpositions are fragile. Thermal noise destroys them, The brain is warm, wet and chaotic. Quantum coherence should last femtoseconds, far too brief to influence neural processing. But recent work in quantum biology has found quantum effects persisting in photosynthesis and bird navigation despite thermal noise. The question isn't whether quantum effects occur in biology. They do. The question is whether they're relevant to consciousness. Testing this directly is extraordinarily difficult. You can't measure quantum states in living neurons without destroying what you're trying to observe. Indirect approaches look for signatures that would distinguish quantum processes from classical ones. A 2024 study found evidence of superradiance in networks of tryptophan, a quantum effect in a biological context at physiological temperatures. This doesn't prove consciousness involves quantum mechanics. It proves quantum effects can survive in environments where they theoretically shouldn't. But even if consciousness does involve quantum processes, the explanatory gap remains. Quantum mechanics describes probabilities and measurements. It doesn't explain why measurements feel like anything. Moving consciousness to the quantum level doesn't solve the problem. It relocates it. Some theories abandon the attempt to derive consciousness from physics entirely. They invert the relationship. What if consciousness is fundamental and physical reality emerges from it? This isn't mysticism. It's an attempt to take subjective experience seriously as a starting point, rather than something to be explained away. Maria Stream's framework treats universal consciousness as a fundamental field. Space, time, and matter arise through symmetry, breaking, and differentiation within this field. Individual conscious experiences are localized excitations. The mathematics parallels quantum field theory, with consciousness playing the role that quantum fields play in particle physics. Physical laws become constraints on how consciousness can differentiate itself. This solves the hard problem by denying its premise. There's no mystery about how physical processes produce consciousness, because physical processes are already within consciousness, but it creates new problems. If consciousness is fundamental, why does brain damage affect it so precisely? Why do specific neural correlates exist? And how do you test a theory that places consciousness at the foundation of reality rather than as something that emerges? These frameworks, information integration, global broadcast, quantum processes, consciousness, first metaphysics, aren't just competing explanations. They're competing about what counts as explanation. Integration theory says consciousness is information structure. Workspace theory says it's functional access. Quantum theories say it's non-computable physics. Consciousness-first theories say it's the only thing that doesn't need explanation because it's the basis from which everything else derives. None of them explain why their proposed mechanisms feel like anything from the inside. They describe correlates, identify structures, map dynamics, but the explanatory gap persists because physics, regardless of which framework you use, describes systems from the outside. It specifies what happens, not what it's like for anything to happen. This might not be a failure of current physics. It might be a feature of physical explanation itself. Physics works by abstracting away from particular instances to general laws. It describes types, not tokens, patterns, not particulars. But consciousness is irreducibly particular. The redness you experience isn't a type. It's a specific instance of experience happening now, to you. Physical theories can't capture this particularity because they are designed to eliminate it. You can know everything about neural firing patterns, information integration, quantum states, and still face the question, Why does any of this produce the specific quality of redness I'm experiencing right now? The question might be unanswerable, not because we lack data, but because physical theories operate at the wrong level of description. They describe objective patterns. Consciousness is subjective presence. These might be genuinely different kinds of things that can't be reduced to each other. Not because we haven't tried hard enough, but because the reduction is conceptually impossible. This leaves us with options, none of them comfortable. Physics might be incomplete in a way that future theories could address, or consciousness might require explanation in terms that physics can't provide. Or the demand for explanation might itself be confused, asking questions that don't have answers in the way we expect. What remains certain is that our most powerful framework for understanding reality encounters something it can't fully grasp. Whether that something is a phenomenon requiring new physics or a category error in how we frame the question remains unresolved. The gap between what we can measure and what we actually experience hasn't closed, and it's not clear it can. The difference between describing how something works and explaining why it feels like anything at all becomes clearest when physics tries to map consciousness onto its existing frameworks. Every physical theory provides a language for describing systems, their structure, their dynamics, the information they contain and transform. These descriptions achieve extraordinary precision. They predict outcomes, specify correlations, map causal chains across scales from quarks to galaxies. But when applied to consciousness, something shifts. The descriptions remain accurate, the correlations hold. Yet the central question, why these particular physical arrangements produce subjective experience, remains untouched. This isn't a gap that more data can close, it's structural. Physics describes systems from the outside, specifying their objective properties and behaviours. Consciousness is irreducibly first person, accessible only to the subject experiencing it. No measurement, however precise, can access what it's like to see red from the perspective of the person seeing it. You can map every neural firing pattern, track every information flow, specify the complete physical state of a brain. None of that tells you what the experience feels like from within. Information theory offers one attempt to bridge this gap. Integrated information theory treats consciousness as a specific type of information structure, one that's both highly differentiated and unified. The theory provides a mathematical measure, phi, quantifying how much integrated information a system contains. A high phi value indicates consciousness, low phi indicates its absence. This framework explains certain puzzling observations. The cerebral cortex, with its 17 billion neurons, supports consciousness. The cerebellum, with 69 billion neurons, doesn't. The difference lies not in neuron count, but in connectivity architecture. The cortex forms a dense web, where every region influences many others. The cerebellum consists of parallel processing modules that rarely interact. Integration theory predicts this distinction. More neurons don't guarantee consciousness if they're organized as isolated computational units rather than a unified network. But describing the conditions that correlates with consciousness isn't the same as explaining why those conditions produce experience. Phi measures information integration, but why should integrated information feel like anything? The theory identifies a necessary structure, perhaps even a sufficient structure, for consciousness to occur. It doesn't explain the presence of phenomenal qualities. Why does seeing red feel different from hearing middle C, even if both involve comparable levels of information integration? The theory describes what consciousness does. It integrates and differentiates information. It doesn't address what consciousness is from the inside. Global neuronal workspace theory takes a different approach. Rather than focusing on integration per se, it emphasizes functional access. Information becomes conscious when it's broadcast globally across the brain's processing systems, making it available for decision-making, language, and memory. Unconscious processing remains local, confined to specialized modules. Conscious processing involves widespread availability. This explains many empirical findings. Why does attention matter for consciousness? Because attention selects which information gets broadcast. Why does consciousness seem unified, despite the brain's modularity? Because global broadcasting creates a shared informational space, accessible to multiple systems simultaneously. Yet the same explanatory gap remains. Describing the functional role of global broadcasting, what it does, which systems it connects, doesn't explain why global access feels like anything. You could imagine a system with all the same functional properties: information broadcast, attention mechanisms, working memory, that nonetheless processes everything in darkness, with no subjective experience accompanying the computations. The theory specifies correlators of consciousness with impressive accuracy. It doesn't close the gap between correlation and explanation. This gap appears regardless of which physical framework you adopt. Quantum theories of consciousness, whether focused on microtubule coherence, quantum computation, or resonance with the zero-point field, face identical problems. They propose mechanisms that might be necessary for consciousness, structures that classical physics can't capture. Suppose quantum coherence in neural microtubules does play a role in conscious processing. This would be a significant discovery, requiring revision of how we understand brain function. But it wouldn't explain why quantum coherence produces subjective experience, rather than just different computational capabilities. The same information processing operations could conceivably occur without any accompanying phenomenology. Recent experiments have tested whether quantum effects occur in biological structures under physiological conditions. Some evidence suggests they do. Quantum coherence has been observed in photosynthetic systems, and superradiance has been demonstrated in networks of tryptophans at body temperature. These findings challenge earlier assumptions that biological systems are too warm and noisy for quantum effects. But even if quantum processes are confirmed in neural structures, the explanatory gap persists. Quantum mechanics describes physical states and their evolution. It doesn't contain a principle explaining why certain quantum states should be accompanied by experience, while others aren't. Consciousness-first theories attempt to dissolve rather than solve the problem. If consciousness is fundamental rather than emergent, then asking why physical processes produce it becomes the wrong question. Physical processes don't produce consciousness, they occur within it. Space, time, and matter arise through differentiation of a universal consciousness field. Individual experiences are localized excitations. This framework eliminates the explanatory gap by reversing the explanatory direction. But it creates new puzzles. If consciousness is fundamental, why does brain damage affect it in such precise and predictable ways? Why do specific neural correlates exist at all? And how do you empirically test a theory that places consciousness at the foundation of reality rather than as something that emerges from physical interactions? The persistence of these problems across different theoretical frameworks suggests something deeper than temporary ignorance. Physics succeeds by abstracting from particular instances to general patterns. It describes types, not tokens, laws, not individual cases, but consciousness is irreducibly particular. The specific quality of redness you're experiencing now isn't a type. It's a unique instance happening to you. Physical theories eliminate this particularity by design. That's what allows them to identify universal patterns. But consciousness might be precisely the aspect of reality that resists this abstraction. Consider what physical explanation achieves. It specifies objective patterns, regularities that hold across instances, relationships between measurable quantities. These patterns allow prediction and control. They reveal structure, but structure itself doesn't contain experience. You can know everything about the neural dynamics underlying pain, which neurons fire, how signals propagate, which neurotransmitters are released, without that knowledge containing the feeling of pain itself. The feeling isn't an additional fact about neural dynamics that we've somehow missed. It's a different kind of thing entirely, one that doesn't appear in objective descriptions, no matter how complete they become. This creates a conceptual impasse. Either physics is missing something, some principle or property that would bridge the gap between structure and experience, or the demand for explanation is itself confused. Maybe consciousness and physical process are genuinely different kinds of things that can't be reduced to each other. Not because we lack sufficient knowledge, but because the reduction is conceptually impossible. The question, why does this physical process feel like anything, might be like asking, what does the colour red weigh? A category error disguised as a legitimate question. Neither option is satisfying. If physics is incomplete, what could the missing element be? What kind of property or principle would explain why certain information structures produce experience while others don't? No one has articulated a plausible candidate. If the question is confused, why does it seem so natural and unavoidable? The gap between objective description and subjective experience doesn't feel like a linguistic confusion. It feels like a genuine mystery about reality. The uncertainty principle illustrates a different kind of limit in physics, one that's fundamental rather than practical. You can't simultaneously measure position and momentum with arbitrary precision because the act of measurement itself disturbs the system. This isn't a limitation of our instruments, it's built into the fabric of quantum reality. Consciousness might represent a similar kind of principled limit, but of a different sort. Not a limit on what we can measure, but a limit on what objective description can capture. Physics maps the objective structure of systems. Consciousness is the subjective presence that accompanies certain structures. These might be genuinely orthogonal, related but irreducible to each other. If that's correct, the explanatory gap isn't temporary. It's permanent, not because we're stupid or lack data, but because physics operates at the wrong level of description for addressing certain questions. This doesn't make consciousness unreal or unimportant. It suggests that reality contains aspects that require different modes of understanding. Physical theories describe what happens. They don't, and perhaps can't, explain what it's like for anything to happen. That distinction might not be crossable, not due to current ignorance, but due to the fundamental nature of explanation itself. What remains is uncertainty. Physics continues advancing, identifying new structures, and correlates. Consciousness remains irreducibly present, resisting complete capture by objective frameworks. The gap between them hasn't closed. Perhaps it can't. Yet something strange happens when physicists attempt to apply information theory to consciousness. Integrated information theory proposes that conscious experience corresponds to integrated information, quantified by a mathematical measure called phi. The theory begins with phenomenological axioms. Consciousness exists intrinsically, has compositional structure, specifies particular states over others, unifies disparate elements, and defines what is and is not part of the experience. From these starting points, IIT derives requirements for the physical substrate. Consciousness, it claims, requires not just information, but information that's causally effective and irreducibly integrated across the system as a whole. The framework offers precise predictions. Consider the cerebellum, a brain region containing roughly 69 billion neurons, more than the cerebral cortex itself. Despite this numerical superiority, the cerebellum contributes nothing to conscious experience. IIT explains this through architecture rather than quantity. The cerebellum's neurons operate in parallel modules with minimal crosstalk. Information flows through separate channels without significant integration. The cortex, by contrast, exhibits dense interconnection. Signals from distant regions converge, interfere, integrate. This architectural difference, according to IIT, determines which structure generates consciousness and which does not. The theory makes phi measurable, at least in principle. Calculate the information a system generates beyond what its parts generate independently. That difference, that irreducible integration, quantifies consciousness. A photodiode contains information, but no integration. A network of interconnected nodes, if sufficiently complex and unified, might cross a threshold. Consciousness becomes a matter of degree rather than kind, present wherever integration exceeds zero. This mathematical precision represents a genuine advance. Previous theories gestured toward complexity or information without specifying how to measure them. IIT provides equations, but the equations describe structure, patterns of causal influence, degrees of integration. They don't contain experience itself. You can calculate phi for a neural network. Without that calculation, explaining why the network feels like anything, the number quantifies integration. It doesn't bridge the gap between integration and sensation. Global neuronal workspace theory takes a different approach. Rather than focusing on intrinsic integration, GNWT emphasizes functional broadcasting. Information becomes conscious when it's globally accessible, when it can influence decision-making, language, memory formation, and other high-level processes. The brain contains specialized modules for different functions. Most operate unconsciously. Conscious states arise when information from these modules gets broadcast widely, entering a global workspace where it becomes available for flexible cognitive use. This framework aligns with attention and working memory research. When you consciously perceive something, neural activity associated with that percept spreads across the cortex. When perception occurs without awareness, subliminal stimuli, unattended objects, activity remains localized. GNWT predicts that consciousness correlates with widespread neural ignition rather than local processing depth. A recent adversarial collaboration tested IIT and GNWT against each other directly. Theory proponents agreed on experimental design beforehand, specifying divergent predictions. Participants viewed visual stimuli while neural activity was measured through multiple methods: fMRI, magnetoencephalography, intracranial recordings. The results supported neither theory cleanly. Both made accurate predictions in some domains and failed in others. Conscious perception correlated with posterior cortical activity more strongly than frontal regions, suggesting that sensory processing matters more than previously assumed. But neither theory's account of why these correlations exist proved decisive. The experiment revealed something more fundamental than which theory wins. Both theories succeed at describing correlates, neural patterns that accompany consciousness. Neither explains why those patterns produce experience. IIT maps the structure of integration. GNWT maps the dynamics of information access. These descriptions become increasingly refined. They locate where consciousness occurs, when, under what conditions. But the how, the mechanism by which physical processes generate subjective presence, remains elusive. Quantum theories attempt a more radical break. Orchestrated objective reduction, proposed by Roger Penrose and Stuart Hameroff, locates consciousness in quantum processes within microtubules, protein structures inside neurons. The theory connects consciousness to quantum superposition and its collapse. During superposition, quantum systems exist in multiple states simultaneously until measurement forces them into one definite outcome. Penrose argued that this collapse might not require external observation, but could occur objectively through gravitational effects at sufficient scales. Hameroff suggested that microtubules might sustain quantum coherence long enough for orchestrated collapse to influence neural firing. The theory faces immediate objections. Quantum coherence typically requires extreme isolation, temperatures near absolute zero, systems shielded from environmental interference. The brain operates at body temperature in a biochemical storm. Thermal noise should destroy quantum superpositions in femtoseconds. OR requires that biological structures maintain coherence despite conditions that seem incompatible with quantum effects. Recent experiments probe this boundary. Studies have detected quantum optical effects in microtubules at physiological temperatures. Anesthetics, which eliminate consciousness, alter these effects. Networks of tryptophan molecules within proteins exhibit superradiance, a quantum phenomenon where photons are emitted collectively rather than independently. These findings don't confirm or cure, but they challenge the assumption that quantum effects are impossible in warm, wet biological systems. Still, even if quantum processes occur in neurons, their relevance to consciousness remains uncertain. Quantum mechanics governs electron behavior in every molecule. Finding quantum effects in the brain doesn't explain why brains generate experience, while other quantum systems don't. The theory must specify what's special about orchestrated collapse versus ordinary quantum dynamics. It must explain why this particular quantum process produces consciousness when countless others don't. Another quantum approach shifts focus from computation to fields. Rather than quantum processing within neurons, this framework proposes that consciousness emerges from the brain's resonance with the quantum vacuum, the zero-point field that pervades all space. Quantum field theory describes empty space not as nothing but as a seething substrate of virtual particles and field fluctuations. These fluctuations have measurable effects. The Casimir force between nearby metal plates arises from vacuum energy. If the brain's architecture allows it to couple with these fluctuations, consciousness might emerge from this interaction rather than from neural computation alone. The proposal connects to criticality, the brain's tendency to operate near phase transitions where small perturbations trigger large-scale reorganization. Conscious states correlate with neural avalanches, displaying power law statistics characteristic of critical systems. This criticality might enable macroscopic quantum effects through coupling with the zero-point field. Cortical microcolumns, the brain's basic functional units, might resonate with vacuum fluctuations in ways that generate conscious experience. This theory raises profound questions about consciousness and fundamental physics. If awareness couples to the quantum vacuum, then experience isn't merely emergent from neural complexity. It's connected to space-time structure itself. Consciousness becomes woven into reality at the Planck scale rather than arising later as a biological accident. The proposal echoes philosophical traditions viewing consciousness as fundamental, but attempts to ground these intuitions in physics. Yet the mechanism remains unclear. How would macroscopic brain structures coherently couple to quantum vacuum fluctuations? What distinguishes this coupling from similar processes in non-conscious systems? The theory gestures towards an explanation without providing sufficient detail to evaluate it rigorously. Consciousness-first theories invert the entire framework. Instead of deriving consciousness from physics, they derive physics from consciousness. Maria Strummer's model treats consciousness as the fundamental field. Space, time, and matter emerge later through processes analogous to symmetry breaking in physics. Individual experiences arise from a universal consciousness through differentiation mechanisms, quantum fluctuations selecting discrete states from an underlying continuum. This approach parallels concepts in quantum gravity and cosmology, where space-time emerges from more basic structures. If classical space-time is emergent, perhaps consciousness is the deeper substrate from which it emerges. The theory aligns with Wheeler's participatory universe and Bohm's implicate order framework, suggesting that observation and reality co-construct each other. The model makes claims about death and identity. If individual consciousness differentiates from a universal field, dissolution at death represents return to the source rather than annihilation. Personal boundaries become temporary configurations within a larger unity. These implications extend far beyond standard neuroscience, but attempt formulation in mathematical terms compatible with physics. The problem again is testability. The theory proposes predictions in physics, neuroscience, and cosmology. But translating consciousness-first claims into empirical tests proves difficult. If consciousness is truly fundamental, what experiments could distinguish this from emergence? What observations would confirm or refute the framework? All these approaches, information theoretic, quantum, consciousness first, share a common feature. They recognize that standard physics doesn't explain experience. Each proposes an extension, modification, or inversion of physical theory to accommodate consciousness. Yet none has achieved consensus or decisive empirical confirmation. The field remains fragmented, uncertain. This fragmentation might indicate immaturity, consciousness science in its infancy, lacking the conceptual tools needed for breakthrough. Or it might reflect something deeper. Perhaps the explanatory gap isn't temporary. Perhaps physics, as currently structured, cannot cross it. Return yourself to what physics achieves. It maps objective patterns, regularities holding across instances, relationships between measurable quantities. These patterns enable prediction and control. They reveal structure, but structure doesn't contain the feel of things. You can specify every neural dynamic underlying pain without that specification containing pain itself. The feeling isn't an additional fact about neurons that we've overlooked. It's a different kind of thing, one that doesn't appear in objective descriptions regardless of their completeness. This creates a conceptual impasse. Either physics is incomplete, missing some principle that would bridge structure and experience, or the demand for bridging is itself confused. Maybe consciousness and physical process are genuinely different kinds of things that can't reduce to each other, not from insufficient knowledge, but from conceptual impossibility. The question, why does this process feel like anything, might resemble asking, what does red weigh? A category error disguised as legitimate inquiry. Neither option satisfies. If physics is incomplete, what's missing? What principle or property would explain why certain information structures produce experience while others don't? No one has articulated a plausible candidate. If the question is confused, why does it seem so natural? The gap between objective description and subjective presence doesn't feel like linguistic confusion. It feels like genuine mystery about reality. Physics continues advancing. Theories identify new correlates and structures. Consciousness remains irreducibly present, resisting complete capture by objective frameworks. The gap hasn't closed. Perhaps it can't. What remains is observation without resolution, a recognition that some aspects of reality might require modes of understanding orthogonal to physical explanation. Not because we're limited, but because explanation itself has boundaries built into its nature. This tension isn't resolvable through better measurement. It's categorical. The problem surfaces when we examine what physical theories actually capture and what they leave out. Physics excels at modelling systems through variables, position, momentum, energy, entropy. These variables relate to each other through equations. The equations predict how systems evolve. When predictions match observations, we say we understand the system. This method has extraordinary reach. It describes planetary orbits, chemical reactions, nuclear decay, quantum interference. Success breeds confidence that eventually all phenomena will yield to similar analysis. Consciousness presents a different challenge, not because it's complex, complexity is tractable, but because it involves properties that don't appear in physical descriptions. Consider pain. You can map every neural correlate, the C fibers firing, neurotransmitter cascades, activation patterns in the insula and anterior cingulate cortex. You can predict behavioral responses, measure reaction times, track learning curves. The physical account is complete on its own terms, yet it contains nothing about what pain feels like. The raw sensation, the quality of suffering, qualia in philosophical terminology, doesn't appear anywhere in that objective description. This isn't ignorance waiting for more data. It's a structural feature of how physics describes things. Physical theories deal in quantities and relations. They specify how much, how fast, in what configuration. They don't specify what anything is like from the inside. The very grammar of physics excludes first-person properties. Information theory seemed promising as a bridge. If consciousness correlates with information processing, perhaps understanding information flow explains experience. Integrated information. Theory formalizes this intuition. It proposes that consciousness corresponds to integrated information, systems where parts influence each other in specific ways generate experience proportional to that integration. The theory provides a mathematical measure, phi, quantifying how much information a system integrates beyond what its components produce independently. IIT makes testable predictions. It explains why the cerebral cortex supports consciousness, while the cerebellum, despite having more neurons, doesn't. The cortex has dense interconnections. The cerebellum's architecture is modular, with parallel channels that don't integrate. IIT predicts that disrupting cortical integration eliminates consciousness, which matches observations during anesthesia and vegetative states. The theory identifies what physical configurations should and shouldn't generate experience. But here's what it doesn't do. It doesn't explain why integrated information feels like anything. The theory maps structure to consciousness. Certain organizations have 5 values above 0, therefore they're conscious. This is correlation with mathematical precision. It's not explanation of why structure produces experience. You could accept every prediction IIT makes and still ask, why does hi-fi equal awareness rather than just complex processing without any accompanying feel? Global neuronal workspace theory takes a different approach. It emphasizes function over integration. According to GNWT, information becomes conscious when it's globally broadcast across multiple brain systems, making it available for reasoning, speech, memory formation. Consciousness is information accessibility, the difference between processing that stays local and processing that gets amplified across the workspace. This framework also generates predictions. It suggests that prefrontal and parietal regions, which coordinate broadcasting, are essential for consciousness. It explains the distinction between subliminal perception and conscious awareness. Information processed without reaching the global workspace remains unconscious. The theory aligns with cognitive neuroscience findings about attention and working memory, yet GNWT faces the same explanatory gap. Why does global broadcasting create subjective experience? What is it about making information widely available that generates the feeling of seeing red or hearing a melody? The theory describes functional architecture brilliantly. It doesn't address why any architecture, no matter how sophisticated, should be accompanied by experience at all. A recent large-scale study directly compared IIT and GNWT. Researchers designed experiments where the theories made divergent predictions about which brain activity patterns would correlate with conscious perception. Neither theory fully succeeded. Some predictions held, others failed. What emerged was complexity. Consciousness correlates with multiple patterns: integration, broadcasting, feedback loops, synchronized oscillations. No single principle captures it completely. This empirical result matters. It suggests that consciousness might not reduce to one elegant mechanism, or it suggests that what we're measuring, neural correlates, is downstream from whatever actually generates experience. Correlates identify where consciousness happens. They don't explain how structure becomes feeling. Quantum theories of consciousness attempt a more radical move. Penrose and Hameroff propose that consciousness involves quantum processes in microtubules, protein structures, inside neurons. Quantum coherence, they argue, enables computations that classical physics can't perform. When quantum states collapse through objective reduction, a gravitational effect on superpositions, conscious moments arise. The theory is speculative. The main objection has always been decoherence. Quantum effects require extreme isolation. The brain is warm, wet and noisy, exactly the environment where quantum coherence should instantly collapse. Recent experiments have found quantum effects in biological systems under certain conditions, including possible quantum states in microtubules. This doesn't validate the consciousness connection, but it challenges the assumption that quantum biology is impossible. Even granting quantum processes in neurons, the explanatory gap remains. Why would quantum computation generate experience? Classical computation doesn't. What makes quantum processing special in this regard? Penrose suggests that consciousness requires non-computable processes, and quantum mechanics provides them. But non-computability doesn't equal consciousness. Many physical systems exhibit non-computable behavior without being aware. Alternative quantum approaches propose that consciousness couples to the quantum vacuum, the zero-point field permeating space. Cortical structures might resonate with vacuum fluctuations, producing the synchronized dynamics associated with conscious states. This framework connects neuroscience to quantum field theory in novel ways. It suggests consciousness isn't purely neural, but involves interaction with fundamental fields. These ideas are provocative. They're also difficult to test. The quantum vacuum exists. Its effects are measurable through phenomena like the Casimir force. Whether brains can couple to it coherently, and whether such coupling would generate experience, remains unclear. The theory expands the explanatory framework, but doesn't solve the core problem. It relocates consciousness from neurons to quantum fields without explaining how fields feel like anything. Consciousness first, theories invert the entire structure. Instead of deriving consciousness from physics, they treat consciousness as fundamental. Physical reality emerges from consciousness rather than the reverse. This approach parallels quantum mechanics interpretations, where observation plays a constitutive role. It resonates with philosophical idealism, the view that mind precedes matter. One recent formulation models universal consciousness as a fundamental field. Individual experiences arise through symmetry breaking, analogous to how distinct particles emerge from unified fields in physics. Space and time become secondary structures generated by consciousness differentiating into localized perspectives. The theory attempts mathematical formulation using concepts from quantum cosmology and information theory. This framework makes death less absolute. If individual consciousness emerges from and returns to a universal field, dissolution means reintegration rather than annihilation. Personal identity becomes temporary, like a wave on an ocean. These implications extend far beyond standard science, touching metaphysics and spirituality. The problem is testability. How do you verify that consciousness is fundamental? What experiment distinguishes this from emergence? The theory proposes predictions, but translating consciousness first claims into empirical tests proves difficult. If consciousness truly precedes physics, what within physics could possibly confirm that? The framework might be true, but unprovable within scientific methodology. All these approaches, informational, quantum, consciousness first, recognize that standard physics doesn't capture experience. Each proposes an extension or modification, yet none has achieved consensus. The field remains fragmented, uncertain. This might indicate immaturity, consciousness science in early stages, lacking proper tools, or it might reflect something deeper about explanation itself. Return to what physics achieves. It identifies patterns, regularities holding across instances. It maps relationships between measurable quantities. These relationships enable prediction and control. They reveal structure. But structure doesn't contain the feel of things. You can specify every neural dynamic underlying joy without that specification containing joy itself. The feeling isn't an additional fact about neurons that we've overlooked. It's a different kind of thing, one that doesn't appear in objective descriptions regardless of completeness. This creates genuine impasse. Either physics is incomplete, missing some principal bridging structure and experience, or the demand for bridging is itself confused. Maybe consciousness and physical process are genuinely different kinds of things that can't reduce to each other, not from insufficient knowledge, but from conceptual impossibility. The question, why does this process feel like anything, might resemble asking, what does red weigh? A category error disguised as legitimate inquiry. Neither option satisfies. If physics is incomplete, what's missing? What property would explain why certain information structures produce experience while others don't? No one has articulated a plausible candidate. If the question is confused, why does it seem so natural? The gap between objective description and subjective presence doesn't feel like linguistic confusion. It feels like genuine mystery about reality. Physics continues advancing. Theories identify new correlates, structures, mechanisms. Consciousness remains present, irreducible, resisting complete capture by objective frameworks. The gap hasn't closed. Perhaps it can't. What remains is observation without resolution, recognition that some aspects of reality might require modes of understanding orthogonal to physical explanation. Not because we're limited, but because explanation itself has boundaries built into its nature. The universe contains both what can be described from outside and what can only be known from within. Physics handles the former with extraordinary precision. The latter might lie permanently beyond its scope, not as failure, but as the natural limit of what third-person methods can reach. Consider how certainty functions within physics. A theory succeeds when it specifies what will happen under defined conditions. Equations become reliable tools because they describe patterns that persist across observations. The reliability isn't absolute. Quantum mechanics introduce fundamental probabilistic limits, but within those limits, prediction works. Systems behave according to rules we can map, test, and use. Consciousness fits awkwardly into this framework. The correlations exist. Specific neural patterns accompany specific experiences. Damage to particular brain regions eliminates corresponding capacities. Anesthesia reliably disrupts awareness. The physical dependencies are clear and consistent. What remains unclear is whether these dependencies constitute explanation or merely correlation at a different level of detail. The distinction matters because correlation describes coexistence without specifying mechanism. When two phenomena regularly occur together, we can predict one from the other without understanding why they're linked. The prediction has practical value. It doesn't satisfy the deeper question about what connects them. Every theory we've examined, information integration, global broadcast, quantum processes, consciousness-first metaphysics, provides increasingly refined descriptions of what accompanies consciousness. None explains why accompaniment occurs. This might indicate that we're looking in the wrong place. Perhaps consciousness isn't the kind of thing that physical theories can explain, not because physics is deficient, but because explanation has natural boundaries. Physics describes objective patterns, structures and dynamics that any observer could verify through measurement. Consciousness is irreducibly subjective. It exists only as experienced by someone. These might be genuinely different categories that can't reduce to each other, not temporarily, but permanently. If that's correct, the explanatory gap isn't a puzzle to solve, but a limit to recognize. The limit doesn't make consciousness unreal or unimportant. It suggests that reality contains aspects requiring different modes of understanding. Physical theories map the objective world with extraordinary precision. They might not be designed to capture what it's like to experience that world from within. This conclusion unsettles because it implies that complete understanding might be impossible in principle. We're accustomed to viewing scientific progress as asymptotic, approaching truth through incremental refinement. The possibility that some questions lie outside this progression, not from ignorance but from the structure of inquiry itself, challenges that narrative. It suggests that reality might be fundamentally partitioned into domains that can't fully translate into each other. Yet the alternative, that physics will eventually explain consciousness once we identify the right mechanism, faces its own problems. Every proposed mechanism describes structure. None contains the experiential dimension that needs explaining. The gap persists regardless of whether we locate consciousness in neurons, microtubules, quantum fields, or universal consciousness. Moving the explanation to a different physical level relocates rather than resolves the core issue. Perhaps both positions are partly correct. Physics might explain much more about consciousness than it currently does, identifying precise mechanisms, predicting which systems generate experience, understanding how different experiences relate to different structures. These advances would constitute genuine progress, but they might still leave the central question untouched. Why any physical structure, no matter how precisely specified, should be accompanied by subjective presence? This residual question might not have an answer within physics, not because the answer is hidden somewhere we haven't looked, but because physical theories operate at the wrong level of description. They describe systems from the outside. Consciousness is what it's like to be a system from the inside. These perspectives might be irreducibly different, related but not reducible. What remains then isn't a solution, but a clearer understanding of the problem's structure. Physics maps the objective world. It identifies patterns, specifies relationships, enables prediction. It does this with unprecedented precision and scope. But precision and scope don't automatically extend to every aspect of reality. Some aspects might require different tools, different languages, different modes of inquiry. The recognition that physics might have limits isn't a failure of science, it's a clarification of what science is and what it does. Physics succeeds by abstracting from particular instances to general laws. This abstraction is its power, but consciousness might be precisely what resists abstraction, the particular instance of experience happening now to someone. No general law captures that particularity because generality eliminates it by design. This leaves us with uncertainty, not the uncertainty of incomplete data, but the uncertainty of genuinely open questions. The relationship between physical structure and conscious experience remains unclear. Multiple frameworks propose different answers, none conclusive. The debate continues because we lack decisive tests. We might always lack them if the question itself lies outside empirical resolution. The gap between what physics can describe and what consciousness involves hasn't closed. It might never close. Not because we're missing information, but because the gap reflects something fundamental about the relationship between objective description and subjective experience. They might be genuinely different kinds of things that can't fully explain each other. What physics achieves is extraordinary. It maps the objective world with precision that would have seemed impossible centuries ago. It reveals patterns, identifies mechanisms, enables technologies that transform how we live. This success is real and profound. But success in one domain doesn't guarantee success in all domains. Reality might contain aspects that third-person methods can't capture, not temporarily, but permanently. Consciousness might be one such aspect, not because it's mysterious in a supernatural sense, but because it's first person in a way that objective description can't reach. The experience of seeing red, feeling pain, being aware, these might require understanding from within that no external description can provide. Physics describes what happens. it might never fully explain what it's like for anything to happen. This isn't defeatism. It's recognition that different questions might require different approaches. Physics hasn't failed by not explaining consciousness. It's done exactly what it's designed to do: map objective patterns with unprecedented accuracy. The fact that subjective experience doesn't reduce to those patterns might tell us something important about both physics and consciousness. They might be complementary aspects of reality that can't fully translate into each other's terms. The universe contains both what can be measured from outside and what can only be known from within. Physics handles the former with extraordinary precision. The latter might lie permanently beyond its scope, not as limitation, but as natural boundary. Recognizing that boundary, understanding what physics can and cannot explain, might be as important as any answer it provides. Some questions remain open, not because we haven't found solutions, but because the questions themselves might exceed what any third-person framework can address.